Well, hello everyone. Let's get started with today's lesson, lesson 7, polar and non-polar bonds. So get out those study guides and let's start. All right, lesson 7, polar and non-polar bonds. All right, so I'm going to do a quick review on electronegativity. Remember that electronegativity is the ability of an atom to attract bonding electrons in a covalent bond. And so the bigger the electronegativity value, the more attractive the atom is to the bonding electrons. And these do have to be bonding electrons involved in a covalent bond. And some extent, even an ionic bond, which we'll discuss at a later point. Okay. So we looked at electronegativity values last time, and we said that as we move across the periodic table left to right, the electronegativity values are increasing, and as we're moving down the periodic table top to bottom, the electronegativity values are decreasing, okay? So increasing left to right, decreasing top to bottom, okay? And I'm not going to go back into all the details of that. You can go back and review your notes on that. But for today's lesson, it's important to understand that each element does have an electronegativity value. And so that when two elements are bonded together to one another, the differences in electronegativities between those two atoms can result in consequences to the type of covalent bond that is actually made or formed. All right. So I want you to keep that in mind. Again, the differences in electronegativity between atoms forming covalent bonds will result in a different type of covalent bond. Okay. All right, so let's get into the results of electronegativity differences. First of all, if you have a covalent bond and electrons in that covalent bond are being shared equally between the two atoms, then we're going to have a non-polar covalent bond. All right, and that's only going to result if the electronegativity differences between the two atoms are essentially zero. Okay, so in other words, if two atoms have the same electronegativity value or nearly the same electronegativity value, then they're going to have an equal sharing of electrons, and there will not be that will result in a non-polar covalent bond. So I mentioned when we talked a little bit about electronegativity in the previous lesson that there's sort of this tug of war match going on between the two atoms for those bonding electrons. And the tug of war essentially is being done because of the difference in electronegativity values. If one element or one atom that's in the covalent bond with the other atom, if the one atom has a higher electronegativity value, it's going to be kind of winning this tug of war battle. And the fact that that atom with the higher electronegativity value is pulling the electrons closer, those bonding electrons closer to itself and away from the other atom. Okay, so again, this tug of war match going on here. So if there is an unequal sharing of electrons, so the two atoms are tug of warring between the two electrons, and this atom over here has a higher electronegativity, so it's going to pull those electrons, winning the battle. What's going to create is an unequal sharing of electrons, and that results in a polar covalent bond. all right? So essentially we have two types of covalent bonds. It's either going to be polar, meaning that there's an unequal sharing of electrons, or polar, or sorry, nonpolar, meaning there's an equal sharing of the electrons, okay? And the only way to really create a polar covalent bond is that there's got to be a pretty good difference in electronegativity values between the two atoms that are forming the covalent bond, okay? So forming a covalent bond that's either nonpolar or polar is going to have some pretty big consequences or results to these bonds, as you're going to find out here and in later lessons. Okay, bonding polarity or polar bonding is a really important concept to understand. Okay, so what we're going to do is we're going to look at some models and some pictures here that represent polar and nonpolar covalent bond going on. All right, so first of all, we have this hydrogen cartoon, you could say, and in this hydrogen cartoon, there is these two hydrogen atoms that are playing tug of war with one another. And they're playing tug of war over a shared pair of electrons. So they essentially got a covalent bond going on here between the two hydrogens. The question is, what type of covalent bond is occurring between these two hydrogen atoms? Is it polar or nonpolar? Well, the question is, what are the electronegativity values of hydrogen? Well, the fact that hydrogen, okay, they're both hydrogens, they're going to have the same electronegativity values, right? So you can think of the fact that because they have the same electronegativity values, both hydrogen atoms, neither one of them can win the tug of war match because they're pulling with equal strength. They have an equal attraction or affinity for these bonding electrons. So in the result, these two hydrogen atoms will have an equal sharing of the electrons and therefore a nonpolar covalent bond. We can also represent this by drawing two hydrogen atoms, and let's use a dashed line. Remember, the dashed line represents the covalent bond and two electrons being shared. So these two electrons that are being shared between these two hydrogens are done so equally because they have, both hydrogens have the same electronegativity values, okay, resulting in a nonpolar covalent bond, okay? But let's contrast this to a tug of war match between chlorine and hydrogen, okay? Now, chlorine has a larger, if you look at your electronegativity values, chlorine has a much higher electronegativity value than hydrogen. As a result, the chlorine atom is going to be winning this tug of war match. It is going to pull on those electrons with a greater strength than hydrogen, all right? Now, hydrogen is still holding on. It is holding on, maybe barely holding on, but it is holding on with dear life, and it's still, there is a sharing of the electrons, okay? So the covalent bond is still there. However, there's an unequal sharing of the electrons, where the chlorine is getting the electrons more often than hydrogen, okay? And so therefore, as a result, the chlorine hydrogen is forming a polar covalent bond. And again, we can represent this by taking a chlorine with a hyphen between the hydrogen and the chlorine, indicating the covalent bond, okay? But what are the consequences of a polar versus a non-polar covalent bond, right? The consequences are pretty big, all right? If the electrons are being shared equally, the the negative electron distribution is going to be equal. What we mean by that is that the two atoms are going to have a balance of negative charges. They're going to have an equal balance of negative charges. But in a polar covalent bond, there's going to be, because of the unequal sharing, there's going to be an unequal balance of negative charge. So because the chlorine in this tug of war match is winning, it's going to have more negative charge more often than hydrogen. Now, as a result of this, the chlorine is going to have what we call a partial negative charge. The way we would indicate that is by using a fancy little symbol, looks like this. This is known as a lowercase delta sign in Greek alphabet. And because the chlorine is going to have those negatively charged electrons more often, chlorine is going to form a partial negative charge. And so we would use this fancy little symbol with a negative sign representing a partial negative charge on the chlorine. The hydrogen, on the other hand, is going to form a partial positive charge. All right. And as a result, we refer to this as a polar covalent bond because we're forming two extreme poles. One is positive, or I should say over here is negative, that's the chlorine. Over here is positive with the hydrogen. All right, so that's why we call it a polar covalent bond, because we're changing the charge distribution. There's an unbalance of negative charge. Most of the negative charge now is over with chlorine and leaving hydrogen with a partial positive charge, okay? Whereas the tug of war match between the two hydrogen atoms, because they're sharing equally and there's an equal distribution of charge, there is no polar or poles created, no partial negative or positive charge because of the equal sharing of electrons. So that's why it's called a non-polar covalent bond, okay? Now, in the middle here of our cartoon, what is represented by this oval here is what we call electron distribution, and it mainly is showing the orbital overlaps. So remember that one atom and the two atoms orbitals that have the two electrons that are being shared, they're going to overlap their orbitals, okay? And so because of this egg-like overlap of orbitals, you could say, the egg-like gives us an equal distribution of electrons. So whenever you see the shape of two orbitals overlapping, there's an equal sharing. I'm going to put the two electrons right there, equally shared in between these two atoms. You get this nice egg-like orbital overlap, okay? Kind of structural representation. Contrast that with the polar covalent bond. You don't get a nice egg-like or overlap situation that occurs. And that's because the chlorine is going to have those electrons closer to itself more often than the hydrogen will. And so that means that there is going to be this larger density of negative charge over here, which is indicated by the bigger shaped orbital, versus the hydrogen has a little bit smaller shaped orbital, meaning there's less of a negative charge and more of a partial positive charge here. All right. So where the egg part is bigger, fatter, I guess you could say, that's where there's more negative charge, and where it's skinnier in the orbital overlap, it's going to be more positive charge. okay? So hopefully that makes sense. And again, all of this is electron density. And we're just kind of saying where most likely are we going to be finding the two electrons being shared. It goes back to thinking about electron density. We talked about orbitals, and we said, where's the highest probability that we're going to find an electron? Well, here we're saying, where's the highest probability that we're going to find the two bonding electrons in this covalent bond? Are we going to find them equally distributed? Are we going to find them more towards one atom or more towards the other atom? In terms of the chlorine hydrogen, we're going to find there's going to be a higher electron probability distribution or a higher probability of finding the bonding electrons with chlorine than with hydrogen. That's all we're saying. Okay, so hopefully that kind of makes sense about the distribution of electrons here. We'll get more into that in just a second. All right, so as we mentioned before, there is going to be, in a polar covalent bond, an unequal distribution of negative and positive charge, okay? So we're going to create the two poles, and as a result, we do form a positive or slightly positive charge versus a partial negative charge. So going back to our chlorine, let's say this is our hydrogen and chlorine bond here, okay? And because of the unequal sharing of electrons, the chlorine is going to create a partial negative charge and the hydrogen a partial positive charge. So we're going to have a higher distribution, right, of electrons over here, and over here it's just going to be a very small distribution, okay? We can connect those together like so. So most likely what this is indicating is we're most likely going to find most of the time these two bonding electrons with chlorine and less of the time with hydrogen. But nevertheless, they're still sharing, just unequally, right? Okay, so finally, let's finish up with talking about dipoles and a little bit more about this electron distribution. Okay, so what exactly do we mean by a dipole? Now remember the term di, di means two. And so we're talking about two poles, okay? In other words, something that's creating a positive and negative charge on different ends of the scale, different poles, okay? So a polar covalent bond is going to form what is called a dipole. Dipoles are really important to understand because we're going to be dealing with dipoles throughout the year as we look at an uneven distribution of negative charge, okay? So we had defined a dipole as an uneven distribution of charge, and the dipole size, so how big the distribution of charge, the difference, is going to be based on an increasing in the difference in electronegativity. So two atoms that have very different electronegativity values, then the difference is very big, you're going to have a bigger dipole. And so that one side of the molecule or one side of the bond becomes way more negative than the other side and becomes more positive. And so we have extremes, okay? Now, if you think about it, what would be the most extreme dipole would be an ionic bond, right? Where the nonmetal is completely negatively charged, right? And is an anion, whereas the metal is going to be completely positive charged and creating the cation. They bond together, but we essentially create an extreme dipole between those two ions. So an ionic bond is an excellent example of a very large dipole difference. all right, between positive and negative charges. But in a covalent bond, as extreme. So the atoms are still sharing electrons, but they just might not be sharing them quite equally. So it does create a dipole, but maybe only with partial positive and partial negative poles. Okay, so how do we represent a dipole? Well, we're going to use an arrow notation to do so. So let's go back to looking at our hydrogen and chlorine. So our hydrogen way over here, and our chlorine is going to be way over here. And this is a long covalent bond, okay? So we're going to represent using this dipole arrow. It's an arrow that's pointing to the most electronegative atom, okay? The arrow always points to the most electronegative atom. Since chlorine is that, it's pointing towards chlorine. To let us know that this is a dipole arrow, we're going to use a line that's going to go down that arrow, and that way you can distinguish this arrow from any other type of arrow that we might use in chemistry. All right, so this is a dipole arrow. And of course, where the arrow is pointing to the most electronegative atom, that is also going to be where you're going to find the more negative charge side of the bond. And the other is going to be more positively charged. And this creates our extreme or two dipoles, positive, negative, and positive. Okay. Hopefully that makes sense here, I hope. All right, so one last look at it with our hydrogen and chlorine, okay? Notice that the egg shape is not evenly distributed, right? So this tells us that because the larger portion of the overlap of orbitals is kind of over here with the chlorine, it's going to tell us that the chlorine is partially negative, and over here, because the overlap is smaller, it's going to be partially positive. And I'm going to draw in a dipole arrow. There's my arrow. I'll put my line down it, and that again points to the most electronegative atom. Okay, and we'll always point the dipole arrow to the most electronegative atom. That's critical. Okay. And therefore the most electronegative atom is going to be positive or negative, sorry, or at least slightly negative. And the other side is going to be slightly positive or positive, okay? Now, because of the egg distribution, these orbital overlaps are showing that there's more negative charge over here based on the bigger oval shape here, right? That means that this region is known as an electron-rich region, okay? There's an excess of negative charge over here. Whereas over here, where it's getting smaller, okay, this is the electron-poor region of the bond, okay? So what we would say is that hydrogen is more electron-poor and chlorine is more electron-rich. Okay, so this idea of electron poor and electron rich is going to be important later on as we get more and more into bonding and more into characteristics of bonding, okay, and into the molecule and the properties and so forth and so forth. Okay, so a couple things I want you to walk away here with before we finish is that when you have two elements that are forming a covalent bond, if there's a big electronegativity difference between the two atoms, there's going to be an unequal sharing of electrons. That results in a dipole, okay, and therefore a polar covalent bond. Anytime we have a dipole, we will either have an ionic bond, which is an extreme dipole, or we will have a polar covalent bond, which we have a partial dipole, right? partial negative and partial positive, okay? So those are the only two real results that can occur with creating a dipole, okay? Either ionic bonding or polar covalent bonding, okay? If there is no dipole, meaning that there's an equal sharing of electrons, then we do not create a excess of positive or excess of negative at all, okay? The charge is evenly distributed, and both atoms basically have an offset or balanced amount of charge, okay? Hopefully this all makes sense. Don't forget the dipole arrows. Don't forget the partial negative charge signs as well. All right. Other than that, that wraps up this lesson. We will spend a lot more time later on here in this unit talking about polar and nonpolar bonds and the direct consequences for that, okay? But that is it for this particular lesson. So we'll see you later.